this video, we're going to cover section 1.11, activated complex theory. The concept of equilibrium is central to the activated complex theory, or as it's also known, the transition state theory. This theory provides a theoretical description of reaction rates. Let's consider the following bimolecular reaction, where A and B react to form an activated complex that undergoes decay, resulting in product formation. As you can see in this figure, the activated complex is the region near the potential energy maximum, and the transition state corresponds to the maximum itself. Now, when this theory was first proposed, experiments were incapable of following reaction dynamics on such short time scales, such that evidence for an activated complex corresponding to the transition state was not available. However, recent developments in experimental kinetics have allowed for the investigation of these transient species. In particular, time-resolved electron diffraction and time-resolved X-ray diffraction have been used to produce what's known as molecular movies. The primary assumption of the activated complex theory is that an equilibrium exists between the reactants and the activated complex. With this in mind, we can develop an expression for the rate of product formation. For the preceding bimolecular reaction, the kinetic mechanism corresponding to the activated complex model is shown, where these expressions represent the equilibrium between the reactants and the activated complex AB double dagger and the decay of the activated complex to product. With the assumption of an equilibrium between the reactants and the activated complex, the differential rate expression for one of the reactants, A in this case, is set equal to 0, consistent with equilibrium. As a result, an expression for the concentration of the activated complex can be obtained. We see here that the change in the concentration of A with time, we can equate that to 0, and the two terms that express that change in the concentration of A in our mechanism can also be equated to 0. In doing so, we can rearrange this expression for the concentration of the activated complex. And what we find is that we end up with a quotient of the two rate constants multiplied by the concentration of A and the concentration of B. This quotient of rate constants, you'll recall, we've equated this to the equilibrium constant. So in this context, this becomes the equilibrium constant associated with the reactants and the activated complex. Further, we can now express the equilibrium constant in terms of the concentration of the activated complex divided by the product of the reactant concentrations. So if the rate at which the products are formed are proportional to the concentration of the activated complex, we can write the following, where the rate of the reaction being equal to the change in the product concentration with time, if this is proportional to the concentration of the activated complex, which we'd expect because in the previous slide, we see that is the activated complex concentration that is decaying to product with a rate constant K2. So we can now equate the overall rate of the reaction to this expression of the equilibrium constant with the activated complex and the original concentrations of the reactants. Now, the full activated complex theory gives an estimate of the constant of proportionality, and it gives that estimate as the following quotient. We have KBT over H. KB represents the Boltzmann constant, T is temperature, and the italicized H is the Planck constant. As a result, we can now equate the rate of the reaction to this proportionality constant multiplied by the equilibrium constant for the activated complex with reactants and the initial concentrations of A and B. So what we're building up here is we're trying to determine what in fact the rate constant is dependent upon. So by comparing this equation to the rate law expression for a second order reaction type 1, that is two different reactants, A and B, the apparent or effective rate constant can be defined as following, where the rate constant is now equal to those terms, the quotient, kBT over H, multiplied by the equilibrium constant with the activated complex. So this is the main result of the activated complex theory, and it provides an important connection between the rate constant for product formation and the molecular parameters for species involved in the reaction. Now, the results of the activated complex theory can also be connected to thermodynamic descriptions of chemical reactions. So recall from thermodynamics that the equilibrium constant K double dagger is related to the corresponding change in Gibbs energy using the following thermodynamic definition, where the difference in the Gibbs energy between the transition state and the reactants is equal to the molar gas constant times temperature and the natural logarithm of the equilibrium constant. With this definition for K, the rate constant now becomes kBT over Planck multiplied by e to the minus delta G double dagger over RT. In addition, the free energy can be related to the corresponding changes in enthalpy and entropy using this expression. Substitution yields the iron equation, and now we see that the rate constant can be equated to terms that include the entropy and enthalpy of that reaction. Notice that the temperature dependence of the reaction rate constant predicted by the activated complex theory is different than that assumed by the Arrhenius expression. Specifically, the pre-exponential term in the iron equation demonstrates a temperature dependence as opposed to the assumed temperature independence of the corresponding term in the Arrhenius expression. Nevertheless, both the iron equation and the Arrhenius expression provide an expression for the temperature dependence of rate constants. As a result, one might expect that the parameters in the iron equation, specifically the change in enthalpy and the change in entropy upon reaching that activated complex, can be related to corresponding parameters in the Arrhenius expression, that is, the activation energy and the pre-exponential factor. So let's look at that in more detail. To derive this relationship, we begin with defining the experimental activation energy as follows, where we have the activation energy being equal to an RT term plus a difference in the internal energy between the transition state and the reactants, this delta U double dagger. Using the thermodynamic definition of enthalpy, one can write the following, where the difference in the internal energy between the transition state and the reactants is equal to the difference in the enthalpy between the transition state and the reactants minus a change in the product of the pressure and the volume between the transition state and the reactants. For a solution phase reaction, unimolecular or bimolecular, the pressure is constant and the change in volume is negligible, such that we can roughly equate the change in internal energy to that of a change in enthalpy. And so the activation energy in terms of enthalpy becomes the following, where EA is equal to a change in the enthalpy between the transition state and the reactants plus RT. So again, for solution phase reactions, whether they're unimolecular or bimolecular, the change in volume is going to be very, very insignificant. As a result, in this expression, this term will go to zero, which basically equates these two terms to one another. As a result, we can substitute this expression into this earlier expression to give us our final activation energy in terms of enthalpy and this other term, RT. Now the rate constant for the solution phase reactions becomes the following, where the rate constant is equal to this pre-exponential term, which includes our entropy of activation. But now we can substitute in for the enthalpy of activation with this new expression, EA minus RT. And if we multiply through, we can separate out two exponential terms. One, which reduces to simply 1, or e to the 1. This being a constant, we can include this in the pre-exponential factor. As a result, the Arrhenius pre-exponential factor now becomes the following, where it's equal to e to the 1, or simply e, the Boltzmann constant, and temperature, the product of those three terms, over the Planck constant, multiplied by e to the delta S double dagger over R, or that change in enthalpy of activation. So here we have a description of the Arrhenius pre-exponential factor in terms of a thermodynamic property, that of entropy. Now, for gas phase reactions, the situation will be slightly different, and that's what we'll look at next. So for a gas phase reaction, the pressure volume term is proportional to the difference in the number of moles between the transition state and the reactants. And this will depend on whether the reaction is unimolecular or bimolecular. So recall that the product of pressure and volume is equal to nRT. And so we're going to focus on what delta N is for each of these two scenarios. So for a unimolecular reaction, there is no change in the number of molecules. We start with a single reactant, and we expect at the activated complex, at that transition state, there to be also a single molecule. Whereas for a bimolecular reaction, as the two reactants approach the activated complex, there will be a reduction in volume, such that the change in the number of moles will be equal to -1. So these two different situations presents two different activation energies, equations for them, as well as the pre-exponential factors. So for a gas phase reaction, which is unimolecular, we expect, according to the activated complex theory, for the activation energy to be equal to the change in the enthalpy of activation plus RT. And the pre-exponential factor will include a factor of e to the 1, as we saw for reactions in solution. For a bimolecular gas phase reaction, however, the activation energy is going to be equal to the change in the enthalpy of activation plus 2RT. And when we use this expression to solve for the pre-exponential factor, we end up with a constant of e to the square. Now notice that both the Arrhenius activation energy and the pre-exponential terms are expected to demonstrate a temperature dependence. That is, temperature is found in this expression, as well it's found here in this expression. Now, if the difference in the enthalpy of activation, if this term is greater in magnitude than the RT term, then we would expect the temperature dependence of the activation energy to be modest. So again, if RT, if it's a small value relative to the magnitude of this term, we don't expect a significant dependence on temperature. Also, the pre-exponential factor is shown to be proportional to the difference in the entropy between the transition state and the reactants. So if there are strict orientational requirements as the reactants approach the activated complex, the transition state, then we would expect the delta S double dagger term to be strongly negative. This represents a decrease in disorder or an increase in order between the transition state and the reactants. So as the reactants are forming the activated complex, if that new activated complex is more ordered than the original reactants, then we would expect a negative term with respect to the change in the entropy of activation. If this is the case, if there's strong orientational requirements needed for the activated complex to form, we expect that term to be very negative, and as a result, the pre-exponential factor will be also quite small. So if you have any questions about the activated complex theory or how it will be used in carrying out calculations for these various terms, by all means, send me an email. Thank you.